Okay, so now we have this general description of the state machine. So how is this actually implemented in the PDP-8 vacuum tube computer? Like what circuit does it take to do this stuff? So now there's no real schematics for this computer. Instead, there are a bunch of Verilog-like files. And so I'm going to flip the screen to show you what is in a Verilog file. Like, how does it do this defer one state? Remember, we said it does defer one only if it's an indirect memory instruction and it was in fetch two state. So if it's in fetch two state, we want it to go to defer one, but only if it's an indirect memory instruction. So how is that described in the source file? And we can even draw out the equivalent schematic here, but I'll show you first the file, and I'll put a link to the file in the description here, but let me show you the file first. So here is the file up here, if I can find the scroll for it. And it has a little module statement here, you can see, sort of like Verilog. Okay, and then a little down here below, we can look and see, like I named, okay, here is the little equation that defines when is going to do defer one. So this is the D input to the defer one flip-flop. That's what this is saying. Okay, the underscore means that this is an active low signal. All right, and then here's the little Boolean equation. And you can see all this looks like a NAND gate, right? A NOT, and then some AND terms. So this is basically just a 3-input NAND gate, okay? This term here says, okay, it must have been in fetch 2 state. So the fetch 2 Q, the Q means that it's the output of the fetch 2 flip-flop. And if there's an A or a B or a C on it, it just means it's a buffered, because there might have been lots of fan outs. This fetch 2 Q state is used lots of places, so it needs a buffer in it to give it bigger fan out. But this is just saying, okay, fetch 2, it was in the fetch 2 state. And this mem inst is another NAND gate or something like that. That's just a 1 if it's a memory reference instruction or a 0 otherwise. And then this MQ, this isn't the MQ register like on a PDP-8. It's a bad name I gave it, but it's the memory bus coming from the Raspberry Pi. So it's the output of the Raspberry Pi. It would be the outputs of the Raspberry Pi going to the tubes, the data bus for it, bit 8. Okay, and I number them starting at the least significant on the right is 0, and the most significant is 11. So this is the MQ8 would be the indirect address bit. So this says defer 1 is going to be next if it's a fetch 2 state currently, and there's a memory reference instruction and a memory reference instruction and indirect. Okay. Now, if we want to look at what memory mem inst is, that must be declared up here somewhere. We'll scroll up a little bit. Yep, sure enough, memory instruction is if it's not both of these top bits set. So that means any of the instructions that begins with a 0 through a 5. If it's a 6 or a 7 at the top, then this mem-inst will be 0. 6 and 7 is for what IoT and the group 1, 2, etc. instructions, right? So this says it's a memory reference instruction. Okay, you got that. And then we can go back down to look at our defer 1 input. And it says, okay, defer 1, again, if it was in fetch 2 state, if it's a memory reference instruction, and with the indirect bit set. Okay, it'll go into defer 1 state. Okay, so that's how all these go. It will go into defer 2 state if it was in defer 1. always. Okay, there's no condition on here. Just if it was in defer 1 state, then it's going to go into defer 2 next. Okay, and likewise for defer 3. If it was in defer 2 state and it is one of those auto increment locations, then it will go into defer 3. Okay, so that's how each one of these states is determined by just it has to be in one of the previous states and then some condition usually based, that's relevant to that state. So if you want, auto index is going to be, checking for that 0010 through 0017 in the memory address register. I guess we could look for that in here somewhere. It's got to be up in here. Oh yeah, so here it is. Auto index, yeah, checks all these memory address register bits, and there, the one with the underscore is the active low, and the one without the underscore is the active high. And so that's how that's determined. So defer 3, okay. Now exact states, these are the 3 that are used to actually execute an instruction here, right? So you have this exec 1 state here. This is the first cycle of any of the instructions, okay, to execute any of the instructions. And here it says first instruction execution cycle, and it follows. Remember the ways that fetching can go from, fetching or somewhere in defer to executing the first cycle of an instruction. Okay, so here are the various outs. Remember, let me flip back to the little page and I'll show you. So remember, there's all these conditions here that puts it into exec 1. So where was that on our little diagram? If you don't remember, here, let me see if I can get it going for you. Remember, we had all these arrows here. So here's one that was going from direct into these exec cycles, right? So you had these 3 different paths here, okay? And actually this is 2 paths sort of overlapped one. It's a direct memory instruction, or it's one of these IoT or group instructions. And the second, and then this path is, if it was a deferred but without auto inc, and then always from deferred 3. So let's go back to our little chart here, or back to the little source file here, and we can see those. There's a fetch 2, and it's not what with direct addressing, or was fetch 2 but it's not a memory instruction. So then, in other words, it's a IoT or one of those group instructions. Or if it was got into defer 2 but it's not an auto increment, then it will go to exec 1. Or finally, if it was in defer 3 state, for the auto incrementing, but it's finishing incrementing the pointer, then it's ready to start executing the instruction. Okay, so that is all those various things, right? And then similarly for exec 2, well, it had to be in exec 1 beforehand. To get to exec 2, you had to be in exec 1 and one of these instructions, okay, because it has to be one of these instructions that requires at least 2 cycles to execute. Okay, the jump instruction, or the group 1 and 2, clear accumulator instructions don't require exec 2, but just exec 1 and one of these instructions. Okay, and I also spoke about the interrupt acknowledge cycle is really a JMS instruction, and JMS takes 3 cycles. So it had, if it was doing an interrupt acknowledge, and now it's basically doing a JMS instruction at this point. So that's why it's that way. And exec 3 is only needed for a TAD, an ISE, or a JMS. So it was an exec 2, and it's about to do one of these 3 instructions, then it will go into exec 3. All right, so that's how these flip-flops go. So we can draw out a equivalent schematic for one of these. It's one that won't take too terribly long, but will show the point. When it goes into That one's kind of long. Defer 1, that's fairly easy. It's just got 3 inputs. So this is just a NAND gate, right? You have 3 variables here and NAND, and it goes to defer 1D. And so we can draw that flip-flop. Let's flip back to the paper here and draw that out. Okay, so to draw that out as a regular flip-flop with a gate, we would draw our little flip-flop here, a D input, a T input for the clock, and that just goes to our common clock signal. Remember, clock 0, CLOK 0. And we have our Q output and Q bar output. Now, what we want this to be is a AND gate. Remember, we had an AND gate. So, and it had to be in fetch 2, so we can put fetch 2Q. So that means that the processor is currently in fetch 2 state, and mem_inst saying, okay, there's a memory reference instruction. Oh, we should label this flip-flop defer 1. Okay, there's a memory reference instruction being loaded in the instruction register, and we also have an indirect bit, which shows up in MQ8. Okay, so if all 3 of those things are true, and then the clock comes along to chunk it into the next state, then it's going to go into defer 1, and this flip-flop is going to set. Now, actually, in the source code, remember here, let me flip it back on here for a second, that this is an active low signal, okay? And it's active low because to make an AND gate takes extra inverter, right? The tube is optimized to make AND or invert gates, and there's always an invert. So if I wanted to make an AND gate, then it would take me 2 triodes to make it, whereas a NAND gate only takes 1 triode. So fortunately, it's very simple to use a NAND gate when you're going into a flip-flop, right? Because all you need to do is, okay, I'm going to make this a NAND gate, and then I just reverse which of these is going to be the defer signal. So this is going to be the positive defer signal, defer 1Q, call this defer 1Q, and this would be my underbar defer 1Q. 1Q. And it just saves me a triode here. I don't need a triode. Why stick an extra triode in here just to flip these around and make it look a little prettier? This will be, you know, 1 fewer triode, and then so it's of course a little bit faster, right? Because I would have to work through that triode to get to this data input on this flip-flop. And now all I have to do is flip these around. So that's why a lot of these signals are active low. I could even write in that this is defer 1D, DEFER 1D, with the underscore meaning, oh, it's an active low. Okay, so there we go. That's how you actually make a circuit out of this state diagram. So see the words here, only if indirect memory reference instruction from fetch 2. Okay, fetch 2, memory reference instruction, indirect bit. And that's how all of these are. Okay, this one here is a always. Okay, it only goes from defer 1 to defer 2. Okay, so that would be just a direct flip-flop there. There wouldn't be any gates or anything on that one, would there? It would be just a direct flip-flop. So your defer 2 or defer 2, the D input is just wired directly to the defer 1 output, and there's your Q and not Q. And of course the clock input always comes from clock 0. so they all clock at the same time, right? And then you get your defer to outputs over here. Okay, so that's it. You have these ones that are simple arrows. Okay, auto ink only. So this defer 3, again, we can look again on the chart or on the source file, but this will have a little AND gate saying, it had to be auto increment as well. Okay, and this is probably a NAND gate because we don't want to waste an extra triode. So let's check that out. We can see down here, okay, there was the defer 2 flip-flop, comes directly from the defer 1 output, and no gate or triode is even used in that one. And then here, yep, here's a NAND gate that says, okay, we go to defer 3 if it was in defer 2 state and the memory address register holds one of those 0010 through 0017 addresses for the auto increment registers. Now, we went through these 3 exec states. Now down here at the bottom of the file, let's just show that briefly. Here's the actual flip-flops coded in here. Here's the actual fetch 3 fetch flip-flops, 3 defer flip-flops, and the execute state flip-flops. This is just buffering, so it just takes an inverter, the active low fetch 2 flip-flop output from over here, and just here runs it through an inverter to get a a buffered output so you can output more, because the design is that these things have a fan out of 10, and if you need 12 or something like that, then you have to buffer it, and that's all that. If you ever see that stuff, that's why you see stuff like that in this code here. So here are all the flip-flops for fetch, and then down here are the instruction register, and it's not really a flip-flop, it's a latch, but there are the bits. Are very similar to a flip-flop, so it's not worth discussing all that much. But here are the state flip-flops, and each one of these has a little LED on it on the front panel board, so you can see what state it's in. And only one of these should be active at a time, right? You shouldn't have 2 of them, and there should never be none. You have to exactly 1 at a time. Okay, so you can think of this too as like a little ring counter, like fetch 1, and then it counts through to fetch 2. Sometimes it skips over some of these though, but normally fetch 1, fetch 2, defer 1, defer 2, 3, and then step through the 3 exec states, and then loops right back around to fetch 1. But a lot of time it skips over some of them. Okay. On average, instructions take like 4.5 cycles, something like that, on average, including the fetch cycles and the execs and the defers and all that stuff. And occasionally, if you get an interrupt request, it'll do int act 1 and then step through 2 exec states and then back to fetch 1. But those are the actual flip-flops. Now, when we were talking earlier about the various states of the execute states, let me flip back to that page real quick here, get that going. We think of the execute states as being really split up based on what instruction it is, okay? But there really is just one flip-flop for exec 1 and one flip-flop for exec 2 and exec 3. So how do we get these various things out of it? And that's just with some simple AND gates. So we'll look at those in the source code here. So this source code here says, okay, we're in TAD 2 when we're really in exec 2 state, and there is a TAD instruction in the instruction register, and that's how we get TAD 2. So we don't have to have a separate flip-flop that would be, 6 gates. A flip-flop is made of 6 gates to get TAD 2. We just have the general exec 2 flip-flop, and then we just AND it with the the fact that there's a TAD instruction in the instruction register, and that gives us TAD 2. So we don't need all these flip-flops. Otherwise, each one of these little states here would have to be its own flip-flop. You know, you'd have what, a couple dozen flip-flops. It seems there are a dozen of them anyway, and that's way too inefficient. Um, and you know, this is drawn kind of funny. This really isn't. It is in a way. It's an AND gate, okay, but it has these active low signals, and yeah, some people don't like active low signals all over the place, but the reason for doing it this way is to save a tube, and every time you save a, or to save a triode, and every time you save going through a triode or an inverter, it's a little faster. So why bother with the additional triode just to make it look a little pretty? So you just have to realize, oh yeah, this is really an AND function, right? You invert the inputs, you invert the output, and you flip the operator. So, you know, this is the active low for exec 2. So you flip that around, that's active high exec 2. And you flip this over, you get active high for it being a TAD instruction. You flip the output, so you get rid of that not sign and. So it's really exec 2 Q and IR TAD without underscores, giving you TAD Q. So that's how all this stuff works. It's, you know, fairly straightforward. At least just have a look at it there. Um, One thing I haven't talked about, okay, so there's the two states for the IO instruction, right? Now, there's group 1 instruction, and group 1 has, or group 2, I'm sorry, has a bit for OR with switch register, and it has a bit for halt, okay? And the tubes wouldn't know what to do with those. So basically they punt it to the Raspberry Pi and say, okay, well this, if they're trying to do a group 2 instruction with OSR or halt, I'm going to pretend it's an IO instruction. So, and it just, the tubes treat it as an IO instruction, say Raspberry Pi, this is an IO instruction, go do it as an IO. And it sort of is, you know, going out to a switch register is really an IO device, and doing a halt where you're halting until an IO device causes an interrupt and that sort of thing. So that's why these OSR and halt the tubes treat it like an IO instruction. Okay. And also for the group 3, those are the extended arithmetic instructions, and they also get treated as an IO instruction. So basically, if it sees a group 2 instruction with either the OSR, halt, or that group 3 bit set, then it pretends it's an IO instruction and just punts it back to the Raspberry Pi. Okay. So this decoding here, if we go look at the, you know, IR IoT, we can see that, oh yeah, it pretends that those other group instructions, yeah, we can see this messiness. Okay, so this here would be the, well, there's a 1, 1, 0, right? 1, 1, 0, decoding the 6 opcode for the actual IoT instruction. Okay, and then here is 1, 1, 1, and then bit 2 is OSR, and 1, 1, 1 with bit 1 being halt, or 1, 1, 1 with bit 0 meaning group 3. Okay, so if it's any of those things, it's going to treat it as an IO instruction. Otherwise, if it's 1, 1, 1 but not an IoT instruction, then it's going to be one of those operate type instructions, group 1 or group 2 without the OSR halt, or group 3 bits set. Okay, so that's a little funkiness in there, but you know, it works and it gets the job done. So that's some instruction decoding circuitry there. Let's see. So that's pretty much how this stuff is put together. So if you want to look to see how any of these bits are derived, it's, you know, simple. There's the data input to the exec3 flip-flop consists of these bits, okay? And again, these equations, they look kind of funny. Why would you do this? Why not just make it an AND? Is to save triodes, right? You want to save as many of the tubes triode elements as you can. And you can take a big and or invert. Like here's this big ugly and or invert statement, right? And or, and then an invert. This is all done with one triode, okay? This big ugly statement is done with one triode. This here looks like there's an embedded NAND term, so this would be two triodes to do this ugly thing here. Let's see, where's a nice big fat one? Okay, so this one here, okay, and or invert. It's all in the and or invert term or form. So this just takes one triode. Okay, a bunch of diodes, but one triode. And that's why this stuff is sort of repeated in here. You say, oh, you should factor this out to be a separate AND gate. Well, then you would have to have two triodes to factor this stuff into an AND gate. And then you would have to AND that in with these various bits and OR it around, and it just makes an extra triode. It makes extra triodes. So it's written this way so that this all fits into exactly one triode element. So you don't have to make lots and lots of tubes out of it to put that together. Here's another thing in and or invert form. Okay, so this is just one triode. There's an OR term. There's an AND term, ORed with another AND term and ORed with another AND term, and then invert. So that's just one triode for this whole thing. Except I just munged it. There, put it back. Okay, so that's again one triode. So that's why these statements might look a little funny. Is just to massage them so that they use the fewest number of tubes. So here's another one. Well, this is just a big NAND gate. There aren't any OR terms, so that would be one triode for that. Okay, one diode for each of the inputs, but one triode in total. Okay, so that's why a lot of these are written this way. Some of them have, let's see, might take two triodes. Okay, like this one here. Okay, this takes two triodes because it's just an AND. So the program that reads this in and generates the tube circuits out of it is going to say, oh, well, this is an AND gate, so I know I can take a NAND gate, but I have to stick an inverter on the output of it. So this is going to take two triodes to make, whereas this only takes one triode to make. All right. So that's why you'll see things like that in here if you have a look at these files. But that's pretty much it. Okay, so that's the sequencer. Now, the sequencer board will also, when it's in a state, okay, a fetch one state, it's going to tell the Raspberry Pi to do a memory read. Okay, so here's the signal that tells the Raspberry Pi, okay, I want you to read. And the signal is generated, okay, fetch, if you're in fetch one state, okay, that's saying, okay, Raspberry Pi, here's an address from the program counter is being sent to you, and I want you to read that memory location. And next cycle, the Raspberry Pi will return the opcode. Or if it's in defer one, it's being sent, the tubes are sending the memory address register to the Raspberry Pi, and the Raspberry Pi should read that and give the pointer value. Okay, arith1, okay, that's a combination of TAD and instruction, arith1. So if it's doing one of the arithmetic instructions, TAD or AND, again, that's going to trigger a memory read. Same with increment and skip if 0. Here's the optimize jump instruction. Remember we said the jump instruction, if there is no interrupt request and you're doing a jump instruction, might as well just start fetching the instruction then. Okay, and same with JMS. So jump and not interrupt request, JMS 3 and not interrupt request, or it said the skip instructions. Okay, so that's group B uh, and not interrupt request. Okay, so that's what this statement is saying. It says Raspberry Pi, do a memory read if you're in any of these states. Okay, and again, it's active low just to save extra triode. Okay, very similar with memory write. As fewer conditions trigger a memory write, of course. You have to be in defer one state and it's an auto increment register, or JMS will write to memory because it wants to write the program counter as the return address. Deposit and clear accumulator, of course. Increment and skip if zero increments a memory location, and interrupt acknowledge is like a JMS instruction, so it writes memory as well. Okay, so that's how these control signals are generated. Okay, various ones. Okay, uh, this one here tells the ALU that it should perform an addition. Okay, and when should the ALU perform an addition? Well, if it's in defer 3 state, okay, it's going to be doing an add to add 1 to increment that pointer value. So the ALU is being used to increment that pointer value. Okay, if it's an exec 3 state, it turns out the exec 3 state is only used for TAD, ISE, and JMS. So it is always going to do an addition for the third cycle of a TAD, of course, because that's the actual addition, right? ISE is incrementing that memory location, that increment as increment and skip if zero. So the ALU is being used to add 1 to the memory location, and for a JMS instruction, the ALU is being used to add 1 to the program counter. Okay, so it is doing an add for any of the time that it gets an exec 3. Okay, and then it's also possible that it's being used to add 1 to the program counter if you're doing a skip instruction and the skip is true. It will be doing an add. Okay, otherwise it's doing an AND operation. Okay, if it's not doing an add and it's not doing one of those, rotate, complement type instructions, group 1 instructions, then it's going to be doing an AND. So basically it's doing an AND by default. Okay, an AND is very quick. Whenever you want to just move something right through the accumulator, you just put ones on one operand, all ones on one operand, tell it to AND, and put the other register you want for the other input to the ALU, and it goes through pretty quick. So AND is the default operation in there. And there's all these others here you can have a look at if you're interested at all. And then here's a control signal. Okay, this says when to update the accumulator, and the things get kerchunked at the end of the cycle, right? So this says load the accumulator with the ALU output at the end of this cycle. So what cycles do you want it to update the accumulator? Well, you want to update the accumulator after it's done the second cycle of an AND instruction, because the accumulator will have the output of the AND instruction ready by the end of that second cycle. For TAD, remember we said that TAD had to do 3 cycles to get the addition done because additions are slow. So you're going to update the accumulator at the end of the third cycle of a TAD. Okay, you're going to update the accumulator at the end of the second cycle of a deposit and clear accumulator, because you want it to put the 0 in the accumulator at the end of the cycle after it's sent the value to the Raspberry Pi, and the Raspberry Pi picks it up just before the tubes start to clear the accumulator. Okay, and then the things like the complement accumulator, those instructions will update the accumulator. The group B, that the skip instructions can also clear the accumulator as well. So if you have that clear bit for the group 2, then that will cause the accumulator to be loaded. And then also I/O instructions. The protocol for the Raspberry Pi is the tubes always send the accumulator and link to the Raspberry Pi, and the Raspberry Pi always replies with the accumulator link and I/O skip. So the tubes know on the second cycle of the IoT instruction to get the updated accumulator and link. If the IO instruction doesn't change the accumulator and link, it just replies back with what it was sent. Okay, so the tubes always load the link and accumulator, and they also possibly increment the program counter as well. All right, and then here, the conditions under which you update the link register and things like that. And here's when you write the program counter. Here's when you increment the program counter under these conditions. Again, these are all and/or inverts, right? These are all in and/or invert form. So they just take one triode to do this mess. Here, this takes one triode to do all this mess. Okay, so that's how that works. Let's see what we got. Now here we got a tilde thrown in the middle here. So this is going to take an extra triode just to invert this signal before it can throw it into and/or invert form. But in general, you try to get it so it's just pure and/or invert form to save triodes. And that's pretty much it. The various control signals are derived based on the state, pretty much. Okay, and there are, again, all the flip-flops. The instruction register is a latch just because latches are only 4 gates instead of 6. And the instruction register can be a latch. Okay, otherwise that's it. That's how the flip-flops are put together, tacked together with all these various gates to make the state machine chug along here. Okay, and one thing about the sequencer board I think I mentioned one place or another is it's a good test, right? You have all this arbitrary logic. You have a bunch of flip-flops. They all have to work. And you have all this arbitrary logic, decoding exec 1. Okay, here's a, and/or invert mess. Oh, there's a little tilde stuck in there, right? So that means there's going to be another little inverter in there, and then an and/or invert, and then here's, again, some more of that stuff. A NAND gate stuck in here with some and or terms, and all that kind of stuff. All of these gates between these various flip-flops, and all that stuff has to work. So the sequencer board is a pretty good general test. If you get that to work, then it's pretty sure that all the rest of the stuff is going to work, because if you look at the memory address registers file or the accumulator file, those sorts of things, those are just pretty much flip-flops and inputs to them. So this shows arbitrary logic between each of the flip-flops, and it has to be able to clock this and clock it reliably, of course. So this sequencer board is a pretty good test of I guess you could say a test of the technology. All right, so that's how the stuff gets actually put together from the state diagram that we drew last one to actually getting it into gates and flip-flops and all that kind of stuff. So again, I hope you were entertained by this talk.